abstraction and misdirection that really, can hinder things. So I'm all pro real-time interaction, but I think that's all I've got time for. Thank you.
Thank the speaker again. So our next presenter is Garbus from the Brandeis University, and he's going to talk about phylogeny-informed interaction estimation accelerates coevolution learning.
Let's see if I can move this away from the top because I have some titles that are kind of relevant. If I move this. Okay, well, we'll just deal with it for now. Hi, everyone. Thanks for being here. Happy to see you all. So today I'm giving a talk titled Phylogeny-Informed Interaction Estimation Accelerates Coevolutionary Learning. This is work done in collaboration with Thomas Wilkins and Alexander Lalangini from the Grand Valley State University in Michigan, and my advisor, Dr. Jordan Pollack. So evolutionary algorithms, as many of you probably know, they typically evolve a single population of solutions, and they select, combine, and randomly mutate solutions across generations of an evolutionary simulation. And because it's a derivative-free optimization method, and it requires no backwards pass like mainstream deep learning requires, but because of this, it requires the evaluation of many, many solutions, and very effective algorithms can typically use large population sizes to great benefit. So coevolutionary algorithms, they extend the evolutionary algorithm paradigm to multiple interacting populations of solutions. And these populations adapt in response to each other through competitive or cooperative interactions, sometimes both. And this kind of results in an arms race dynamic where solutions evolve in response to each other. And this requires even more evaluations to compute fitness and perform selection. And so an example might be a predator chasing a prey. The prey might evolve to be faster. The predator might also evolve to be faster to catch up to the prey. And the prey in response evolves to be even faster. And so because the target, the prey, is constantly adapting, the predator has to constantly adapt as well. So as I mentioned, these algorithms are fairly expensive. And so there's many algorithms that are designed for coevolution, and they typically require what's called all versus all evaluation. And so if you have two populations, let's say each population has 100 solutions, then that's not 100 evaluations, that's 10,000 evaluations, because you have to evaluate each solution against all of its possible opponents. And so in the evolutionary case, there's been a lot of work done on estimation techniques and subsampling methods to accelerate evolutionary algorithms. That way you don't have to do an extensive evaluation or evaluate each individual on each possible problem every single time. So one example is lexicase selection, which typically requires that you evaluate all members of a population against a set of tests. But there are methods that are used to actually avoid having to do all members against all tests. But this assumes that the problem set is unchanging, which is not the case in coevolution. And you also need to make sure that all individuals in a population are sufficiently evaluated. And so with something like a single population case, you can just do, let's say, if you have 100 tests, you can just sample 10 of them every single generation. But with coevolution, it becomes a bit more tricky because you don't want to accidentally sample different amounts of the wrong opponent. And so there's a concept in evolutionary computing and just biology in general called the phylogeny, which is just the tree of life, or the ancestry tree of an evolving population. And so branches of this tree illustrate divergence from common ancestors. And so if two nodes on the tree are siblings that come from the same parent, that indicates that their most recent common ancestor is the parent, and their lineages are going to diverge from that point onward. but all of their descendants will share that same common ancestor of the parent. And this has a lot of other benefits too. There's a lot of insight that phylogenies reveal. There's multiple papers on it. And there's also a tutorial on it as well on on Wednesday, if you are interested. And they are very informative, and there's a lot of benefit to kind of adding them into your evolutionary system without a lot of downside. And so what we wanted to look into is, could it be used to estimate performance on these tasks, specifically for coevolutionary tasks? And so there's some work that's been done by PhylogenyInformed et al. In the evolutionary case. And this is also for lexicase selection, as previously mentioned, where basically with some chance they can sample let's see if do I have my cursor over here? Yeah, we do, okay. When you're evaluating a population, you don't need to evaluate, each member on every single problem. And so you can see over here that for these members, we can inherit their performance on, let's say, the fifth problem over here, or the fifth index of this vector from their parent, F over here. And so we only have to evaluate on a subset of the problems. And this is a zoomed in example of a much larger phylogenetic tree, but I just zoomed it in for clarity over here. And you can actually see that, when you're trying to subsample a lot, or rather a few problems, so you're trying to do mostly estimation, these don't really yield that much improvement. But if you're doing a decent amount of evaluation, so you're not doing too much estimation, but you are still estimating, you can still get modest improvement on this problem. And so we wanted to apply this to coevolution. And so we wanted to use the phylogenies of both populations to estimate the outcomes of interactions between members of those populations. So this is a bit different because the opponents are constantly changing. So performance against one individual might not be indicative of performance against another individual. But if this works, then it enables the use of existing algorithms like lexicase selection in coevolutionary settings without having to do the all versus all evaluation. And it doesn't require that you have to change too much of the subsampling techniques. And this can potentially reduce the number of evaluations required. But it also kind of feels intuitive, right? Like, if Magnus Carlsen can beat me in chess like really badly, like his child will probably be able to beat my child in chess pretty badly too, you know? So it feels intuitive, right? So if this actually works, how does the actual method of choosing interactions to evaluate affect the evolutionary dynamics and the estimation quality? And so we'll cover that matchmaking method in a second, but first we'll kind of describe the approach that we use. So we use a weighted average of the k nearest interactions between a target interaction. So over here, for example, you can see that we're trying to estimate the interaction between A and B. And in this simple example, we have 3 interactions that are actually evaluated, but we only are looking at the 2 nearest interactions. And so we ignore this top interaction between their grandparents, and we look at this interaction between A's parent and B, and A's parent and B's parent. Now, if you were doing an unweighted average, so just a naive average, you would see that this interaction is this results in a score of 2 for A's parent and a score of 0 for B's parent. And this interaction results in a score of 0 for A's parent against B. And so the estimated outcome of A, if you were just doing a normal average, would be 1, because 2 plus 0 divided by 2 is 1. But because we're weighting it by the distance, and because this interaction is closer or more closely related to the target interaction that we're trying to estimate, we actually give this a bit more weight in our setup. And so instead of the score being 1 to 0.5, if we were doing a normal average, we give this interaction over here a bit more weight. And so it actually is estimated to be a tie with 2/3 score for each individual. So we tried 3 sampling methods. So the baseline that we tried is all versus all, which is the method that I described previously, where you just evaluate each member of one population against each member of another population. And so if your population is size n, then you have, this is on the order of O of n squared. We also tried a method which we call random cohorts. Random cohorts basically just divide each population into groups into m groups of size k. And then you take these groups and you pair them up with groups from another population, and you run all versus all between these groups. And this ensures that each member of each population gets evaluated the same number of times as each member of another population. And because you're sampling these pretty randomly, it's a relatively bias-free method. And finally, we tried parents versus all. And so the idea behind this is that you play the parents of each generation against all individuals in the opposing population. And the benefit of this is that whenever you're doing estimation, each estimation has at least 2 high quality relative interactions. There's at least 2 interactions that are only 1 distance away from the target interaction. And so you at least have some of your weighted average as good estimates. So we applied this to 3 domains using 3 different algorithms, and we got kind of interesting results on each of them. So the all experiments that we show here consist of 30 trials. We show kind of the 95% confidence intervals of the means, but there's additional statistical analyses available in the full paper. So the first domain that we try is the numbers game. There's been a lot of different versions of this domain throughout the literature over the years. We are utilizing this variant. There are 2 subdomains, and there's a bit of an important distinction between them. But in the numbers game, you're just basically evolving vectors of numbers, real valued numbers in our case, to rise in value across dimensions. And there's 2 variants called compare on one and compare on all. And compare on one essentially compares on just 1 dimension to see if one individual is greater than another. And compare on all compares on all dimensions. And so an individual must be greater than an opponent on all dimensions in order to actually get a score of 1. And for this domain, we use fitness proportional selection. And so this is kind of what like the dynamics are expected to look like in these kinds of domains for what we're measuring. There's a lot more nuance to this domain. It's actually a very interesting problem, but for the sake of our purposes, we just wanted to see if the dynamics are similar to the all versus all case. And so we can evolve numbers successfully. This does not introduce significant error into our setting. And you can actually see that when you're plotting against the number of evaluations, our methods actually rise in some faster because you require less evaluations per generation. And crucially, we also plot the error of our method. And because the score is a binary 1 or 0, and we use populations of size 100 for this domain, the error actually corresponds to the percentage of individuals that are incorrect. And so you can see that the random cohorts method on average has about a 20% error rate. So 80% of the time it's correct. And the parents versus all method has an error rate of around 16%. This is where things start to get interesting. And so for the compare on all domain, this is actually an interesting domain because there's this failure case, which is actually possible, known as a disconnect, where if one population is so much greater than another population across all dimensions, then there's no way for an individual in the lesser population to beat an individual in the greater population, even through random drift. And so the random cohorts method, which is bias-free, works as expected, but the parents versus all method, which chooses individuals based on if they were selected in the previous generation, actually introduces some amount of error into the system that is biased such that the populations can actually disconnect. And so you see this kind of plateau over here But what this plateau actually is it's trials becoming more and more disconnected one by one. So across 30 trials, you actually see this disconnection phenomenon happening where one population becomes so much greater than the other population that there's no more evolutionary gradient to actually follow. The second domain that we tried was sorting networks. So a sorting network is just a network traditionally implemented in hardware, but you can also implement it in software to design the networks. And it sorts a fixed length vector of numbers through a list of comparisons and swaps. And so each swap or comparison is hard-coded for each network. So you can design networks with 65 swaps, with 70 swaps, and there was interest in designing the smallest possible network. And so some seminal work from the coevolutionary literature co-evolved sorting networks by changing the swaps that are in the network with a population of numbers that co-evolved to be harder to swap and to sort. And this actually was able to find a very, very small sorting network. And so that work was utilizing sexual reproduction. Our work only applies to asexual reproduction, but we apply the same domain. And so mutations consist of randomly adding, removing, or switching the order of comparisons to discover better networks. And we also added an additional fitness term to reward perfect networks for being smaller. So once a network perfectly sorts all possible inputs, then we give it extra bonus depending on how small it is. And this actually turns out to be really important too, because in a lot of different domains, there's a lot of interest in having multiple parts of your loss function, especially in the reinforcement learning setting, where you're not optimizing for one thing, but you're optimizing for two things. And so we wanted to see how our method could work with additional fitness terms. And we actually see something very interesting. And so the parents versus all and random cohorts method can both evolve greater networks. They actually do solve the task successfully. But the random cohorts method in this domain actually fails to minimize the network. And so even though they both accomplish the task in terms of beating the opposing population by sorting all the numbers correctly, what we actually find is that the random cohorts method introduces enough error into the domain to actually hurt the second fitness term from doing its job effectively. What happens is that because there's additional error introduced into the system, there are less perfect networks. There are less valid networks that actually can sort all possible inputs. And that reduces the search space effectively of smaller size networks, because you're trying to only search the space of small size networks that perfectly sort all inputs. And so because of this error, it actually performs worse than all versus all in this case, but parents versus all is able to approximate the dynamics with half the compute without actually using or introducing significant errors into the system. And then the last domain that we have is the collision game. This was presented at, I believe, A-Life 2022. And in this domain, agents are controlled by neural networks. So these are dynamically sized neural networks, not fixed architecture neural networks. And there's actually 3 co-evolving populations. And this domain is of interest because this is a very open-ended domain with a lot of potential for arms race dynamics. In the sorting networks in the numbers game, there's not really that potential for an arms race, or at least a constant introduction of novelty. But with the neural domain, there's lots of different strategies that you can do. And so the game basically is just played by 2 agents on a number line, and they have to decide whether they collide or not. And one agent wants to collide, one agent doesn't want to collide, or one agent wants to collide and another agent wants to collide. And you can't tell which agent actually wants to collide with you. And so there are 3 populations called the host, the parasite, and the mutualist population. So the host, they want to collide with mutualist populations and they want to avoid parasites. The parasite wants to collide with the host, and the mutualist also wants to collide with the host. And so the host has to figure out whether the opponent is a parasite or a mutualist. And the parasite and the mutualist are both trying to trick the host, basically, or at least the parasite is trying to persuade the host. The parasite is trying to trick the host. The mutualist is trying to persuade the host. And so you get these kind of what we expect in this domain is we expect evolving unbounded neural complexity, where the networks get bigger and bigger in size, and their strategies get more and more complicated. So very quickly, we see that the genotype sizes, which is what we're trying to optimize for in this domain, actually do increase in size. And so this system works with both methods, but we find something very interesting on this domain, which is that while this method works in regions of lower search complexity, as complexity increases, the all versus all method actually catches up in terms of performance. So we can see that over here, parents versus all in random cohorts, it actually grows our networks. And all of this complexity is adaptive. These networks grow in complexity much faster than all versus all per evaluation. But eventually, as the search becomes harder and harder, you do actually need to have more evaluations to uncover the benefits of different mutations. You can't just estimate them away. And so, just to sum up, phylogeny-informed interaction estimation for coevolution significantly reduces the number of evaluations required for progress across all three domains. For the last domain, which is more open-ended, it reduces the amount of evaluations required for a good chunk of the earlier section. But once you start hitting the ceiling of complexity, it actually reduces in effectiveness. This works with multiple selection methods. So the collision game also used the disco selection method, which I did not detail, but it's a coevolutionary algorithm that operates differently than lexicase selection and fitness proportional selection. And it works for both of those, or all three of those. And at least one sampling method was able to approximate the dynamics of all versus all and perform no worse than it. But as I mentioned, this does appear to reduce in effectiveness as search becomes significantly harder. So just as a reminder, there's a tutorial about phylogenies and how and why to track them in artificial life. That is going to be hosted tomorrow in Auditorium 0, which I think is this room, from 1300 to 1440, or as I say, 1 to 240. Thank you very much for your time.